the kind of the structural engineering aspects of existing buildings, and particularly those buildings that are at risk in Southern California, and also kind of the state and local, requirements, seismic ordinances that are in place, and what's coming up in those areas, and also how to protect these buildings, how to retrofit them. I have a lot of slides, and this can go very deep, but I'm going to try to hit it all really quick, and then we can answer questions later, perhaps, if there's more detailed questions. I'm not going to get too far into this. We all know we're in earthquake country. We've all seen the reports and perhaps heard from Lucy Jones. This is a report that just came out recently. Of course, we know there's earthquake faults all around us. But this report kind of is an update showing, as we see at the bottom here. Is this a pointer? The likelihood of a magnitude 7 earthquake in the next 30 years is around 50%. The Northridge earthquake, for reference, was 6.7, and the likelihood of that is 60%. So we know the earthquakes are going to come. There's no doubt about that. It's just where and when. And when we talk about earthquake magnitudes, it's important to keep in mind, because this is a very common question, that it's not just about the magnitude, it's about the location. So you have faults nearby Torrance, the Newport-Inglewood fault. If an earthquake magnitude 7 occurs there, where we're standing here will receive very heavy shaking. If a magnitude 7 occurs, perhaps similar to like what we had out in Ridgecrest or out in the San Andreas Falls, maybe Torrance is not as affected. So it's important to, when you talk about magnitude, to talk about the distance from the fault and which fault you're talking about. But the earthquakes are coming, there's no doubt about that. So the buildings that are usually most at risk and at risk of severe damage and collapse are these buildings here. There's the unreinforced masonry buildings, non-ductile concrete buildings, pre-Northridge steel moment frame buildings, tilt-up buildings, and soft story buildings. I'll get into all those details now. First, the unreinforced masonry buildings. These are probably the most prone to damage and collapse. But fortunately, there's a lot of strides have been made in protecting these buildings. Unreinforced masonry is just really what you say. It's unreinforced brick, similar to what you see down here. Could be single story, multi-story. And the issues with unreinforced masonry is, first of all, you may have issues where the parapet wants to collapse and fall from the building. And then when an earthquake comes, the ability of those brick walls to handle those seismic forces, usually there's very little connection between the floors, and so you have the risk of the floors collapsing, the walls crumbling. And so similar to what you see here, you have this risk of the walls basically crumbling to the ground and the floors collapsing. Here's some examples. It really started where people learned about this was in the Long Beach earthquake in 1933. This was a school building before, this was after. This is another building in the Long Beach earthquake, even as recent as 2003 in Paso Robles. If you were around during the Whittier earthquake, there were a lot of unreinforced masonry buildings damaged then. In 1986, there was a Senate bill which came about, which required a survey of all the buildings and for jurisdictions to start putting programs into place to retrofit them. That wasn't necessarily mandated or enforced. It's all about the jurisdictions and how well they can enforce it. But for those that did put into place mandatory programs, those buildings have all pretty much been retrofitted and are safe. That represents about 75% of all the building stock in California. So not to say that there aren't unreinforced masonry buildings out there. I know of a few that haven't been retrofitted, so they are out there, but a great majority of them have been retrofitted already. And so I won't get into a lot of the details, but the way that they're retrofitted is usually by putting bracing at the parapet, something shown like this down here, strengthening those connections between the floors and the And the walls, I couldn't find a good photo, but you've all seen brick buildings with the little square plates and a bolt on the outside. That's what that is. And then there's other things too. I want to get into something a little off with my text, but that's fine. Non-ductile concrete buildings. So this is actually a very prominent thing that's being talked about now, especially in the city of LA and a few other cities. Non-ductile concrete buildings are just that. Buildings built before 1971 that have little ductility. When we say ductility, it's the ability to flex and bend and move with the earthquake. These are just some examples of buildings in LA. They don't all have to be big buildings like what I'm showing here. They could be one-story buildings, two-story buildings. And where we learn most is in the 1971 San Fernando earthquake. This is the Olive View Hospital. And this hospital had to be demolished after the earthquake. And this is what taught structural engineers a lot about seismic design. So 1971 is kind of a key turning point for seismic design. And you can see this column here, the issue being the lack of reinforcement. You see in here these horizontal bars. I mean, they're just like small wires. They weren't really able to hold the column together. In current seismic design, we place lots of these and very closely spaced to help the building survive. We even had problems in the Northridge earthquake. This is a building in Santa Monica. These diagonal shear cracks basically are in the columns and really, jeopardizing the ability of that column to support the loads of the building. And this was a building out in the valley, in the San Fernando Valley. So there's all sorts of different types of damages and issues that we have with non-ductile concrete buildings. The city of LA has an ordinance from 2015. They were kind of the forefront of this. This shows you the kind of the timeline. Basically, they start sending out checklists. We've been involved with helping many clients with that. And that's an easy part. That's just identifying whether it is a non-ductile concrete building or not. The next part is the hard part, which is actually putting some plans into place to retrofit the building. And it's all about really economics. It's about how much it's about money and how much it's going to take to do this work. So they give 10 years to get in place a retrofit permit and 25 years to actually complete the construction. And there's some nuances to that we could talk about code changing and stuff like that. It's not as straightforward as it looks. Santa Monica has done a similar ordinance in 2017 and West Hollywood, but they have a little bit shorter time frames. Santa Monica, 10 years to finish it. West Hollywood, 10 years to address the major seismic deficiencies, and then 20 years after that. And then you have other municipalities, Beverly Hills, Burbank, Long Beach, that are in the process, either have voluntary ordinances or working on a mandatory ordinance. Lots of different ways to retrofit these buildings. We could spend a lot of time on this. We use something called structural wallpaper. It's basically carbon fiber, like fiberglass, but using carbon instead of glass, where you can strengthen walls and strengthen those columns. You can wrap it around the column to protect it, like those columns we saw at the Olive View Hospital. We can do things like put a braced frame on the outside to kind of stiffen it up and strengthen that structure. This is a building near the airport you might have seen. This is the braced frame added to the outside of the building to help minimize disruption to the inside. And then they put a cover on it. Beautiful looking building right on Century. So I'm going fast, but I need to cover a few more things. So the pre-Northridge steel moment frame buildings. This is kind of you've seen a moment frame building is basically a series of beams and columns. In a moment frame, you're looking for those beams and columns to flex and be ductile. That's what we saw with the concrete buildings with the lack of reinforcement. With the steel buildings, it had a different issue. Typically, the beam is welded to the column, and these welds, it was an eye-opener for all the structural engineering community during the Northridge earthquake. People started looking at it, a long story about how that actually came about, but started looking into buildings, scraping off the fireproofing in the buildings, and realized all of these fractures that went into the columns from the beams, all originating at those welds. So very large research program was undertaken. That's what I did my research in, and came up with lots of new ways of doing that in new construction. But if you're pre-1994, you're very likely have this problem in your building. So right after the earthquake in 95, the city of LA had basically an ordinance for limited types of buildings and took care of those issues. But since then, really nothing has happened until recently. Santa Monica and West Hollywood have put into place ordinances to address those issues. The way they're addressed, lots of different ways. Some you go in and strengthen the connection. One way is putting a little haunch at the bottom, lots of different ways. Another way is to basically take the moment frame out of play and supplement it with a braced frame, kind of similar to that building I showed near LAX. Another way, this is a project we did in San Francisco where we added a braced frame to help these lower levels, and these are using what we call viscous dampers. They're basically shock absorbers. And so you can see that's the finished condition. These are actually like big shock absorbers you have on your car to help dissipate the energy from the earthquake. Tilt-up buildings. So there's a lot of these in Southern California, a lot of warehouses. We usually think of them as this, but sometimes they're looking a lot nicer, not like such industrial warehouses. They could be in office parks and business parks all throughout Southern California. If you don't know, tilt-up is basically, it's a concrete wall building, but they're cast on the ground, lifted up into place. You've probably seen them in construction, driving around, seeing things like this. The problem, especially after the Northridge earthquake, showed to us that, again, kind of like the unreinforced masonry, the connection of the roof to those walls is very critical. And we learned a lot from that earthquake about what level of force we should be designing those connections for. So there was a lot of, some cases of the building walls collapsing and the roof partially collapsing because of that. And we go back, this is just one small example of you basically go in and add anchors that tie the roof structure or the floor structure better into the walls. But there's no seismic retrofit ordinances in place for these buildings. Generally, if you're after the Northridge earthquake, after 1994, these buildings are probably in much better condition. Pre-1994, that's where those issues will be. Lastly, soft story buildings. I think Ali's going to talk a little bit more about this. We have these buildings very prevalent throughout Southern California. When we say soft story, there's, again, lots of nuances to this, but primarily it's where you have the parking at the ground floor below an apartment building, and you can see all these walls that all of a sudden disappear or set back, and that creates what we call a soft story. And what happens in the earthquake, that soft story has a potential to collapse. These are some photos from the Northridge earthquake. I'm sure you've all seen this before. And very devastating. So that actually has the most ordinances and has gained the most traction, not only because it's dangerous and very devastating, but it's also relatively economical to take care of. City of LA has an ordinance from 2015, shorter duration, because they realize that the exposure, the risk to life is even much higher because this is where people live. Retrofit and plans in place in 2 years, construction complete in 7 years. Santa Monica and West Hollywood have mandatory ordinances, a little bit shorter durations, kind of similar to the non-ductile concrete. And then other cities, including Torrance, have either voluntary or working on mandatory ordinances related to this. This is an example of a type of retrofit. It can use moment frames, shear walls, braced frames. This is a common example where you basically put a steel moment frame around the parking spaces. There's nothing nice and nothing fun and nothing cheap about retrofits, but this is, fairly straightforward to do. Last thing I just wanted to leave all of you with, this is a graph. If this was showing the cost of doing a retrofit versus the gain in seismic performance, there's even if there's no ordinance in place, there's a little bit you can do to help your buildings. If this was the cost curve here, it would cost a certain amount just to protect the building, prevent it from collapsing. And the benefit you get is substantial. Whereas that little more increment to say, let's make the building comply with the current code, let's make it, even better than that, the gain you're getting is marginal. You've already protected life in the building. You've done a lot to keep it from collapsing, but that marginal increase in seismic performance generates a lot of cost. So even by just addressing a few focused things in your buildings, you can actually gain a lot of benefit from that. I think that's all I have. Thank you for your time.
I think maybe we have time for one or two questions if there's anybody in the room. Yes.
When you inspect the building, can you tell what level of earthquake it will respond to, and also once you fix it, what will it respond to?
So by looking at the building, it's very hard to tell. It usually involves calculations and us doing some engineering. So it involves a little bit of work. Usually what we do for owners is what we tell them is, let's take it step by step. We're not going to go all the way to the end, because you may find that, like I said, there's different options. We can do a little bit and protect a certain amount. We can do a lot and protect it even more. But the costs are different. The timelines are different. So what we usually advise people is that we start slow. We start phased. We say, look, let's take a brief look, limited amount of our involvement, and we can then start to guide you from there. But just by looking at the building, it's hard to say other than what I showed you here. And like I said too, you got to not only think of magnitude, but think of all the faults that are around you. Sir.
Thank you very much for the presentation. Now, a lot of us are under impression that if our buildings are built according to newer building codes, or we don't have a mandatory ordinance, then we are safe. Would you elaborate a little bit about code, building code, and seismic performance design?
Sure.
I'm sorry to test you like this. Could you repeat that question into the mic to make sure that it's...
Sure. So what was asked was, if we're designing a building to current codes, a brand new building, what's the expectation in terms of damage or risk to life? So that's actually something that scares me a little bit about what people in the public know about this. What the building code really is trying to do is protect life safety. It's trying to make sure people can exit the building, that the building doesn't collapse. That's what our goal is. It's not, though, to prevent damage. We will see a lot of damage. Brand new buildings are designed to flex and yield and crack and do their work, because it would be far too cost prohibitive to make it so that nothing ever happens in an earthquake. So what people should understand, though, is there will be buildings with lots of damage, cracks, lots of things that need to be repaired, and it's possible that the buildings can't be repaired economically. It may not make sense. It may make more sense to demolish it. But the primary goal of the code is to protect life safety.
And a lot of times with minimal retrofitting, we can increase the performance of the building beyond life safety.
Absolutely.
Put it back to operations faster.
That's kind of what we're trying to demonstrate here. A very little bit of money can actually go a long way in seismic performance.
Thank you.
Thank you. Let's give Dr. Skokan a hand, please.